So this problem actually has conflicting information because it says mu sub s is 0.3, but then it says they're in equilibrium, and that's not going to happen because this block is heavy enough to overcome the friction on that one. However, we can still do some of these parts. Free body diagram. So I googled pulley free body diagram, and here's a wonderful SparkNotes source. So credit to them. Here is the actual diagram. They're using a somewhat strange set of axes, which is different up here than down here, but it actually makes the math easier, I think. In any case, we don't care about their axes too much. The important part is the free body diagram, which is down here. You simply have gravity pointing down and tension pulling up. Because anytime there's a rope pulling, you just call it tension, and then you figure out what the actual... You figure out the tension later, basically, because you never know what tension is until you figure out everything else in the problem that is opposing the tension, because tension just pulls as hard as it needs to. In this case, since the blocks are not moving, they're in equilibrium, tension is going to equal gravity. And that's part 3. So I'm going to go ahead and show that before I talk about the free body diagram of the top block. We have tension upward minus mg downward. That's why it's minus equals 0, because a equals 0. And so the right side of this is F net equals MA. And the A is 0, and so yeah. And so T equals mg. This is, by the way, this M, which is labeled as M2. So this is M2. Yep. So then this top block has, again, there's a rope, call it tension. There's friction. Friction pulls to the left because friction always pulls parallel to the surface. Sometimes people say, oh, the friction pulls up or down. No, friction pulls parallel to the surface. So, and it opposes all the other forces. So there's tension pulling that way, friction is going to pull that way. Now, in this SparkNotes drawing, friction is a really small arrow and tension is a big arrow, but in ours, that's not the case, because they're in equilibrium. So if they're in equilibrium, the friction has to be pulling the same amount as the tension, so those two arrows will be the same size. Gravity pulls down, of course. Normal force pushes up, same strength as gravity, because there's nothing else happening in the y direction. Done with that. So part 2. Relationship between the two tensions. The tensions are the same, they have to be, because the pulley doesn't have any mass. Now, if he ever gave you a mass pulley, a pulley that has mass, then it gets a lot more difficult, and it's probably too hard for a test. But when the pulley has no mass, then these tensions are the same, because it's the same rope. The rope can't stretch. We assume it's a stretchless rope. As I said, T2 is equal to the weight of the box because it's not moving. Now, if the box were falling, this is very important. If the box were accelerating downward, then the tension would be less than the weight of the box because it's letting it accelerate downward. And that's kind of like, you can imagine if someone jumps bungee jumping, there's no tension on the bungee cord until they are slowing down. While they're accelerating, falling downward and accelerating and getting faster and faster, there's almost no tension on the cord. But then when there is tension on the cord, that is going to either keep them at a constant speed or even slow them down. And if the tension is greater than gravity, of course, that's going to slow them down. Write down the equation, part 4. Write down the equations for Newton's second law for each of the two blocks for both the x and y directions. So, I'm going to not use the Spark Notes axes in case I'm just gonna. To me, it seems easier to just stick with normal axes. In case, because I think that's what De Silva would do. So for the bottom block, we have nothing's happening in the y direction. So I don't know, 0 equals 0. Very interesting. I meant to say x direction. And in the y direction, it's gravity pointing down. And tension. Tension 2, I believe, is the label. Pointing up. And it's in equilibrium, so equals 0. M1. The y looks pretty darn similar, only it's for M1 it's the x because it's the rope is pulling sideways. T1. And there's no gravity pulling in the x direction, so let's see, T1, so it's not actually very similar. T1 pulls to the right. What's pulling to the left? Friction. Which we think is static. And in the y direction, we have gravity. I should label these masses. This is M2. This is M1. Because it's gravity pulling down on this block. And what pushes up? The normal force on block 1. And that's all 0. Everything's not moving. Everything's not accelerating. So you could then algebra these, which is what it, I assume, since he says what's the magnitude of the friction force. I don't know how to solve this because I don't know when he says mu s if he wants us to use that or not. So you need to ask him. Done for now, since we don't have enough. We have too much information and it's conflicting.